So let's take the first problem, which looks quite straightforward. It is quite straightforward. I'm going to go through the standard solutions for these four problems, and then if there is time at the end, then I might actually come back and cover a few solutions that are relatively unusual, but we will also reduce them to the same basic problem solving strategies. So implementing merge sort is the first problem, the most straightforward of them, where you are given an array of integers and you have to sort the array using merge sort. So the input is just an integer array called ARR, and the output needs to be the sorted integer array. So there's no mystery about how to solve this problem. We just have to apply the template which you should have learned for merge sort. It's just a straightforward application of that, although I will talk about a couple of changes to it as part of optimizing it. So recall that merge sort is a divide and conquer algorithm, which means that when you are given an array of size n to sort, you take it upon yourself uh, to solve that problem, but you are lazy. So, acting like a lazy manager, you decide to divide the problem into two halves by position. So, basically, you take the left half and you assign it, you hire someone under you to sort the left half, and likewise you hire someone else under you, your right subordinate, who will be assigned the right half. And then when both of them have solved their respective subproblems, then you will do some work at the end to merge their solutions together into the solution for the overall problem. Now, both of these subordinates are also equally lazy, since we assume that all the humans in this corporate hierarchy have the same nature. So they will in turn subdivide their subproblem into two halves and hire two other people under them. And this process continues until we reach some leaf level workers who are given a subproblem of size 1 or maybe 0 to solve, in which case there's nothing further to be done. Okay, so this is how you have to think of merge sort being um, run by this imaginary corporate hierarchy. And you would have learned in your sorting class that when and in your recursion and other classes that whenever you code this up, this divide and conquer strategy, which naturally leads to a recursive implementation, whenever you code this up, you should code up the strategy from the perspective of an arbitrary worker in this hierarchy, who could be an internal node worker like this red node, or could be an arbitrary leaf worker like any of these green nodes. And so instead of thinking about writing the code for this problem from our own perspective as the root manager, we think about first writing a piece of code that everyone in this hierarchy will be executing, including the root manager. And so, what is an arbitrary worker in this hierarchy going to do as part of their job description? That is what we write as the helper function, right? So, the helper function takes a bunch of parameters which essentially make up the subproblem definition for an arbitrary worker in this hierarchy. So if we think of let's say this arbitrary red worker, what is this worker being delegated, right? Maybe there's a path that is longer, but let's just say this worker is located here. What is their manager assigning them? What task is their manager giving them? Uh, well, essentially, this worker is going to get a subarray of the original array to sort. right? And so that's the job description. So that means this subproblem definition for this worker is going to be a subarray of the original array. So if the original array is an integer array called, let's say that's the parameter a, we are going to get a subarray of a, which means we are going to get a reference to the original array with the boundaries of the subarray specified. And these boundaries are specified in a way that um, if the array itself could be larger than this, but the start index and the end index are both included within this subarray. And so this white rectangle is really the subarray to sort. There are obviously more elements on either side, but that's the subarray we focus on. So what will this arbitrary worker in this hierarchy do? Well, that depends on whether this worker firstly is a leaf level worker or an internal node worker. So the first part of the helper function code is always what we should do if the worker happens to be a leaf level worker. That's called the base case. And how do we identify that we are in the base case? Well, if the subproblem size that we are given is very small, let's say just one number or maybe nothing, just a zero element subarray, then we are in the base case, right? So what is a one element subarray going to be? Um, if we imagine shrinking this white rectangle to a single element, that means the start and end indices will coincide. So and if the start index exceeds the end index, then it's like there is nothing there at all, right? So if we think about size 1 or size 0 subproblem, that is the base case, right? If start is greater than or equal to end, that means the subproblem size is 0 or 1. Then there is nothing to do for the leaf level worker. The leaf worker just returns. But on the other hand, if the worker is not a leaf level worker, we call that the recursive case, then we are thinking about a general internal node in this hierarchy. And a general internal node in this hierarchy is going to um, try to be lazy. So their subproblem size is at least 2, which means they will split the problem into two halves around some midpoint. And so we need to calculate what that midpoint is so that we can delegate, we can divide up the problem into two parts and first ask our two subordinates to solve the subproblem, the respective subproblems, and then we will step in and do some work at the end. So we immediately divide the subproblem into two parts around a mid index, which we can calculate as start plus end by 2, the average of start and end indices. But if you've seen some of my earlier classes, you know that if you want to avoid integer overflow, a better way to write this is the same formula. It's just slightly better way to write it in a way that there is no integer overflow, because start plus end, the sum can actually be a very large value, and then when you divide by 2 it comes down back to earth. Uh, but instead of that, if start plus end is going to lead to an integer overflow, um, but start and end individually are valid integers, then this formula allows us to get to the midpoint starting from the start index and moving forward rather than jumping to start plus end and then dividing by 2. So once we have the midpoint identified, let's say this is the mid index, then our left subproblem is going to be everything up to the mid index, and our right subproblem will be everything beyond the mid index. And so we use the mid index to identify the boundary between the left and right subproblems. And so we can immediately hire two people under us and delegate to them the left and right subproblems respectively. How do we do that? Uh, we do that by uh, making two recursive calls. So the first recursive call to our first subordinate, second recursive call to our second subordinate, and within these brackets, we have to specify the subproblem definition for our two subordinates. So our left subordinate gets this blue rectangle. The specification of the subarray corresponding to the blue rectangle is that it is a subarray of the original array A, starting from start index start and ending at the index mid. And likewise, the specification of the yellow rectangle, the subproblem definition for a right subordinate, is that it's a subarray of the original array A, starting from index mid plus 1 and ending at index end. So this uh, this index is mid plus 1. Okay. Now, assuming that our two subordinates have done their work and uh, they come back and tell us that they finished, that means these two rectangles, the blue and the yellow rectangles, have been sorted already. And so our job is to now merge those two solutions together into the overall sorted subarray from start to end. And you would recall this was there in the foundation videos as well as in the live class. The merge part uh, essentially involves two pointers which start from the leftmost elements of both of those subarrays, because essentially we want to create the merged output uh, in a decrease and conquer way, right? What's the first element in the merged output going to be? It's going to be whichever of these two numbers is the smaller number, right? What's the second element going to be? Well, once we know what the smaller number is, we can ignore it because we assume it's already gone into the auxiliary output. So we have a slightly shorter blue rectangle maybe and the original yellow rectangle. So as long as we have our some variable, some pointer pointing to the leftmost element of whatever the remaining two subproblems are, sorry, the remaining arrays to be merged are, subarrays to be merged are, we cannot keep picking the leftmost, the smaller of the two elements to append to our merged output. And so we construct the merged output in an increasing fashion one by one. Um, and the code for that, something I assume you more or less remember. So this is something that you would have covered in part 2 of your sorting live class and as well as in the foundation videos. So we initialize our two pointers, I and j, to start and mid plus 1. And we also have an auxiliary array which is going to store the merged output, because this can't be done in place. We need extra space. So having done the initialization, we have two-pointer pass saying as long as our two pointers I and j are pointing within the bounds of their respective rectangles, that is, as long as I is less than or equal to mid and as long as j is less than or equal to end, we essentially have three cases, right? We want to pick which element goes next into our merged output. So we have three cases. Case one is when a of I is equal to a of j. Case 2 is when a of I is less than a of j. Case 3 is when a of I is more than a of j. So clearly when a of I is less than a of j, we are going to take the smaller number and append it to the growing merged output. So we will append a of I to the merged output and increment the I pointer. Okay, I'm assuming that the auxiliary array here is an empty array list or basically a dynamically resizable array. So it takes a constant time to append an element at its end. And if we have the other case, right, ignore for now what we do when the two are equal, but assuming that we are in the other case where a of j is the smaller number, we are naturally going to append that into the auxiliary array and increment the j pointer accordingly. And when a of I is equal to a of j, we treat it as if a of I is actually smaller than a of j, because if there are, let's say, three twos in the left subarray, and let's say there are two twos in the right subarray, what we want in the merged output is for the three twos to go before the two twos. Right? This is the stability requirement of merge sort, that when there are duplicate elements, they need to appear in the same order in the output as they appeared in the input. And so, how do we ensure that all the blue twos go into the merged output before any of the yellow twos go? Well, we treat the blue two as if it's smaller than the yellow two. So even if it's equal, we treat it as if a of I is less than a of j. And so we do essentially what we were doing when a of I was less than a of j. And so we keep doing this until one of the 2 pointers is going to jump off the right edge of uh, its respective rectangle. And when that happens, the other pointer might still be pointing somewhere inside, right? We don't know whether it's the I pointer that will jump off or the j pointer. That depends on what the numbers are. But we still have to gather together the remaining elements from the subarray that has not yet been exhausted and keep appending that into our merged output. And so uh, the way to do that is to essentially have two since we don't know which pointer is still pointing inside, we consider both possibilities. If the I pointer has still not reached the mid index, I mean, it still hasn't crossed the mid index, that means we have to collect the remaining elements from the blue rectangle. So we basically do what we were doing over here. While I is less than mid, whatever we were doing here, we do the same thing, which is to keep gathering up the remaining elements from the left subarray into um, the auxiliary array and increment the I pointer. The other possibility is that the j pointer is still within the bounds of its respective array. In that case, we do what we were doing over here, right? While j is less than or equal to end, we add e of j into the merged output, and then we increment the j pointer. So this is the gather phase. And at the end, our merged output, which is the auxiliary array, would have exactly as many number of elements as the size of the original subarray from start to end. And so what we do is we um, take the temporary merged output and we copy it back into the original sub array, right? So that I'm just going to do with a single line here in pseudocode, but I assume you can do that in whatever language you're in. In Python, it is actually a single line. So we are saying that the entire subarray from start to end, the original subarray, should be filled with the merged output, right? So in other words, take all the elements of the auxiliary array one by one and copy them back into the original array from start to end. And this completes, you don't need a return, but let's say we have a return statement. This completes the description of the general strategy that's going to be used by an arbitrary worker in this corporate hierarchy. Right? I marked them all in white, but I guess I could have written all this in red. Right? This is essentially what an internal node worker is doing, and that describes the helper function. Right? Now, this is the point where we start thinking about the original problem. The original problem, the overall interview problem, was to do a merge sort given an integer array called ARR. So as the root manager, what am I going to do? I'm not going to do anything different. Since the helper function is written, everyone is executing exactly the same piece of code. I must also execute that same piece of code. I just have to figure out what are the parameters with which I'm going to execute the helper function. So it has three parameters. What's the original array out of, whose subarray I'm looking at? Well, it's ARR. And what are the start and end indices of my subproblem? My subproblem is essentially the whole array. Um, so starting at index 0, ending at index length of the array minus 1. Right? And once I start executing this with these parameters, this entire imaginary corporate hierarchy will be built out in DFS order, if you remember from your recursion class. And so when I come here, the array ARR would be sorted. So I just have to return it. Okay, this is the code for merge sort. Hopefully, this should look familiar. Um, see any questions about this? Will the slides be shared with us? Yeah, I'll send them to operations after this class. Shobit, no. I will get back to advanced graphs. I this is something that I was requested to do. That's why I'm doing this. I didn't understand the last step when we merge the auxiliary array into the original one on every recursive call. Can't we do that in the end only? Uh, Joe, I'm not sure what you mean by can't we do that at the end. We are doing that at the end here. Um, so we can't just keep the temporary output in the auxiliary array, because this, as soon as the function returns, that auxiliary array will be out of scope and it will be garbage collected. We have to copy it back into the original subarray, and only then will the managers that are higher up in the chain pick up their respective subarray, the solutions to their two subproblems, and then combine them together, right? They are not going to look at the auxiliary arrays used by their subordinates to figure out what the elements are. They're going to look at uh, the numbers in the original array. So we need everything back in the original array at the end. Now, having said that, um, one thing you might notice here is that every worker in this hierarchy is creating a fresh copy of a new auxiliary array, initialized to an empty list, I guess, or depending on what programming language you use, you could even initialize it exactly to the same size as uh, the array from start to end. That is, um, the number of elements in the auxiliary array will be exactly end minus start plus 1. But rather than each worker initializing and then having uh, us having to garbage collect the whole thing, we don't know when that garbage collection will happen. So uh, one thing we could do is to optimize this is to allocate this auxiliary array not as a local array that keeps getting allocated and then deallocated, but as a global array to begin with, right? As a global array to begin with. So I'm going to pretend, so I'm going to write a slightly different piece of code here where, let's see, what do we have to, how do we change the code if our auxiliary array is global? What does that mean? It means that if my original array A looks like this white rectangle here, my auxiliary array will also have the same size. Will have the same size as the original array, that is size n. So anytime a worker like this red node here wants to work on their respective subproblem, let's say from start to end, let me draw that in red. let's say this red rectangle is what this red internal node worker is focused on sorting. Um, Actually, this red rectangle belongs to the original array. I guess I should show it that way. Let me redraw this over here. Let's say this red node is getting this particular subarray to sort from start to end. So the auxiliary space that will be used by the red node could be the parallel indices in the auxiliary array. So instead of having to allocate um, a fresh auxiliary array dynamically, the red node is just going to peer into the global auxiliary array from indices start to end and just use it as a temporary slate, temporary scratch pad to write the merged output to, and then uh, copy the merged output back into the original array exactly at those indices. So that's a slightly more efficient way of using the auxiliary space. We just allocate it once, and then that's it. Everyone taps into that same auxiliary array, okay, of size n. So what changes in our code then? Um, well, depending on what language you're using, maybe you have to pass the auxiliary array as a fourth parameter. I'm not going to do that. I'm just going to assume that it's global in scope, or in some languages like Python, the helper function would typically be an inner function, in which case, if the auxiliary array is actually allocated um, outside it, it's going to be accessible within it. So the auxiliary array is just going to be a one-dimensional array of size n. It doesn't matter what it's initialized to, because it's being used as a scratch pad anyway. So we write we make it accessible inside the helper function using whatever technique your language uses, and then we don't need this. We don't need this. Um, Instead, we automatically assume that our auxiliary array is also being used from index start to index end. So that means when I add my first element from the blue and the yellow rectangles into the auxiliary array, it's going to get added at the start index, and then the next element will be uh, inserted at index start plus 1, and so on. So I need to track what index in the auxiliary array am I going to append that next element into. So I can call that as the k pointer, which will track which index in the auxiliary array the next value will go into. So k will also be initialized to start, right? And what else changes? So when we were appending something into the auxiliary array, it was automatically being appended at the end. Here, it's going to be appended, or rather copied, at index k, right? That's the difference. Instead of our array dynamically growing in size, it's already allocated. So we just have to insert it at the right index. So this line will be replaced by um, auxiliary array of k is equal to a of I, right? And obviously when we do I++, we also need to do k++, so that we are ready to insert the next element at index k again. Similarly, this will also look the same when we are inserting it into when we are copying when we are adding the next element from the right subarray into the auxiliary array. We'll do the same thing. We'll do this, and then we'll do k++. Of course, the I++ and j++ are also happening with it, um, right? And the same thing here. This part is going to look like this. and this line will be replaced by that. And when we copy all the elements back from the auxiliary array to into the sub array of the original array, we are not copying everything because the auxiliary array is of size n. We are copying essentially elements from the same parallel indices back into the original array, and then we return. Right. So essentially, we are treating it as a scratch pad into which we write the merged output, and then finally we copy it back to the original array. Any questions about uh, this method? Abhishek?
Hi, Omkar. So, I suppose I had this question from the very beginning, from the sorting week. So, what's the purpose, or let me put it this way: I understand the purpose of auxiliary array, but do we really need it? Because ultimately, whatever after the auxiliary array is created, we ultimately copy it back to the original array.
Yeah,
So,
so we just need it as a temporary scratch pad. We don't need it beyond that. But we can't. We need that scratch pad. Otherwise, we can't run this algorithm in log n time.
So, so we use the auxiliary array when we are in the merge phase.
Yeah,
So that means we are already having two sorted arrays or sections of array with us, which we are
yeah,
trying to merge.
yeah.
Now if we have two pointers, we know the start and the end indices of both the sections. If
Hmm,
we have two pointers,
hmm.
can't we just directly affect the original array by just moving uh, linearly across,
No, no, no. Because if you are inserting some number here, let's say the next number that needs to go in will be from the yellow rectangle.
right?
You'll insert it here. What will you do with the number over here?
Right. So
If you
probably
if you, if you move it there, then it's already out of order. All of these numbers have to stay in order. You can't bring in numbers from here to you know uh,
okay.
into the blue rectangle. There's no space there for for them. So it's only in the auxiliary array that you have. That's why you need the temporary scratch pad.
Okay. So let me ask you this: can we reduce the entire space of the auxiliary array to just one variable?
No, no,
No, that's not possible.
you
Okay.
can't because that variable is not going to be sufficient because what if the next element also comes in from the yellow rectangle there? Then you need another number to be kicked out from the blue. So now then you have two variables. Then you need three, four, right? You can be given an input where there are lots of numbers then that will be kicked out from the blue rectangle, and you'll have to track them all, which is essentially what we are doing in the auxiliary array.
Okay. Okay. Okay.
I
Sure.
mean, we're not kicking out anything. We are just writing the merged output in a separate space. So that
Sure.
way we don't have to kick anything out from the original arrays. We just have our two pointers doing the regular walk.
Sure. Makes sense. Thank you so much.
Okay. So somebody asked about the code. I do have the Python code for both the the regular implementation as well as this modified implementation with an auxiliary array that has the same size as the original array. Right. Um, Uday said, for me, it's better to define auxiliary array inside the helper rather than passing as an argument to helper. Defining as global bag just to avoid maintain. Yeah, I mean, you can pick whatever you want. I'm giving you both options. If the interviewer wants you to use a single auxiliary array instead of everyone in the hierarchy allocating and deallocating, because think about it, if the garbage collection doesn't happen immediately, then what's going to happen is you need an auxiliary array of size n here, of size n by 2 here, n by 2 here, four auxiliary arrays of size n by 4, and so on. So if all of them are going to stay in memory, the total space that the auxiliary array will end up, all the auxiliary arrays will end up using is going to be n log n. So the assumption is that they're immediately garbage collected as soon as the function ends. Now, I hope you also remember the analysis of merge sort, um, which was there in the foundation videos. So I assume I don't have to go through it again. But just in case um, somebody needs it for a quick reference, as a lazy manager, as you know, most of the work, I mean, the work of sorting the two subproblems was done by my subordinates. That's not something I did. All I did is um, calculate the mid index and then delegate the work to my two subordinates, which all this takes just a constant amount of time. And then at the end, after both subordinates had sorted their respective subproblems, this is the point where I stepped in and I did the work of merging those two subarrays together. And so the time complexity of this piece of code is essentially order of the size of my subproblem, right? And the size of my subproblem obviously depends on which level I am at. So at the root manager is going to have a subproblem of size n, right? The two next level managers are going to get subproblems of size n by 2, and since there are two of them, they're going to have collectively doing a doing work that is proportional to n again. Likewise, there'll be four managers at the next level, each of them working on subproblems of size n by 4. So collectively, they will end up doing order n work again. And since this is a complete uh, binary tree, at the last level, assuming we have only subproblems of size 1, how long, what is the height of this tree going to be? Well, at each level, the subproblem size reduces by a factor of 2. So here it was n, n by 2, n by 4, and so on. At the last level, it's going to be n by 2 to the power h, right? Where h is the level number of the last level. So this is level 0, level 1, level 2. So notice that the pattern is that at level I, the subproblem size is n by 2 to the power I. That means at level h, the subproblem size is going to be n by 2 to the power h. And when that becomes equal to 1, that's when we are at the leaf level. So that means n is 2 to the power h, or when we take log base 2 of both sides, we get h is log base 2 of n. So that means everyone in the hierarchy is doing order n work all the way up to level h. So the combined work done by everyone in this corporate hierarchy is going to be n plus n plus n as many times as the height of this tree, which is order of n times log n. And what I just said is, if the garbage collection does not happen, even the space allocated is going to be given by the same expression. So if by allocating it in advance to be, as an array of size n, you don't depend on garbage collection happening immediately. Okay, in interviews, do they expect bottom-up version or top-down recursive implementation? The rule of thumb is if the recursive implementation is easier, which it is in this case, they prefer the recursive version. Uh, Although if there is time at the end today, I will go through the iterative implementation as well. So that's the uh, first problem, which was merge sort. Now let's go to the second problem. And by the way, just to warn you in advance, even though the official time of this class is 2 hours, it might continue up to 3 hours. So the second problem now. Uh, okay, there are a couple of questions. Seema?
you showed two templates, like first one and the second one. Yeah. So which
Yeah.
one do you prefer we should follow? Like
If the
we should.
interviewer doesn't care, it's you can follow the first one. That's you know it's close to the union and intersection problems as you might have seen in the sorting class. So
Okay.
you can follow the first template, although uh, changing it to the second, to using a global auxiliary array doesn't change anything. It just means you need an index here instead of just appending. You
Mhm.
need to keep track of what the next index is in that global auxiliary array. There's So in terms of code length, yeah, it looks like you're adding a bunch of lines. So
Mhm.
if it's okay, you can use. I mean, if it's okay with the interviewer, you can use an auxiliary array
Okay. Sure.
uh,
But both cases
inside.
it is n log n, correct?
Sorry.
Both cases it is
Yeah,
time
the time
complexity.
complexity is the same. Even the space complexity is the same, assuming that, I mean, asymptotically, it's the same. Um Assuming that garbage collection is something that is happening immediately. But if the interviewer is nitpicky, then you can try, working with a global auxiliary array.
Mhm. Sure. Thank you for
Mario?
that.
Hello?
Yeah.
Okay. Yeah, and what about why don't you make use of the fact that we are trying to sort integers, right? And I think we could make use of that property to not have to use auxiliary space, extra space, because we could use the modulus and the integer division to store extra information on the same actual array that we're sorting.
Uh, I'm not sure how that would work in log n time. Um, you're not referring to anything like radix sort, right?
Um, it's kind of like a similar. So instead of using auxiliary space, the approach would be uh, basically you have to first do a first pass to get the biggest element on the array that we're trying to sort, right? And then after we figure out which one is the biggest, then we just in the same array we can store in any slot whatever number we want. For example, if we want to store in a slot 0 of the array number 5, in addition to the number that we already have, we just store 5 times the number that we already have, right? Then if we want to get the 5, we do the division. And then if we want to get the original number, we do the modulus. So we store two numbers in one slot using the modulus and the fact that we know which number is the biggest.
But then you're still using auxiliary space then, right? If you're
No,
storing two numbers.
I mean you're just storing a bigger number multiplied by itself. Uh,
Um,
I think I mean this way of not using extra space is described online. On, you
yeah, so
can Google
maybe
it.
you can take this up offline because I'm not sure how this would run in nlog n time. Firstly, I'm not sure I understood exactly what's happening since what you're describing seems a little subtle.
Yeah,
Um, but
yeah. It's
even
a
if it
little it's a little complicated.
even if it is, it's not clear how it would not end up using more space, given that we are worried about the start and end indices
Yeah,
doing it, having overflow. Um, when you start multiplying numbers and indices together, I'm not sure how that would work without using extra space proportional to the input size.
yeah. Well, I'll post the link on
Yeah,
the
you can
Q&A.
ping me on Discord or
Yeah. Okay.
tag me
Sounds
on
good.
your channel. Yeah, we
Sounds good.
can look at it offline. Yeah, Mumtaz.
Hi, Omkar. Yeah. So my question was, in interviews, do they typically ask you to implement a merge sort or any kind of sort, or is it in the context of some other problem that you'll eventually end up implementing,
Yeah,
a merge sort?
I haven't heard anybody, at least any student, coming back and saying that I was asked to implement merge sort. So this is more, I'm doing this just because it's there in the problem set here.
Okay.
And a couple of, optimized implementations, one of which I've covered, which is to use a global auxiliary array. But
Okay.
yeah,
Thanks. Yeah. I was just wondering because I kind of feel that you've already pretty well described it in the foundation. So yeah. Okay.
Yeah.
Sorry.
Yeah. Okay, folks. I'm just going to take one more question because I know there are 169 of you here, but it's not going to be possible to take too many questions. Otherwise, we won't complete the material. So, Narendra.
Yeah. Can you hear me, Onkar?
Yeah.
Yeah. So you just described that integer overflow when we actually do and minus.
Yeah.
Yeah. So can you help to explain with one example in which case, at what level, or in which case it might fall into integer overflow?
Well, suppose your array size is so huge that the start and end indices. I mean, the array size itself is so huge that the final index, let's say index n minus 1, is very close to the maximum integer, right? Whatever the value is, 4 bytes, or let's say it's close to 2 billion or whatever the maximum integer value is in your language. At some point, merge sort is going to be doing a recursive call where someone is going to get a subarray towards the end of the actual array with start indices, with the start index being somewhere here and maybe this being the end index. So these two indices are close to being, close to overflowing, but not fully, not really hitting the overflow value. But when you add them, if start is close to 2 billion, end is close to 2 billion, their sum will be close to 4 billion, and that would be an overflow, right? Because in 4 bytes, assuming you have both positive and negative values equally represented, you can't go beyond plus 2 billion or something like that.
Right. That maximum number that can fit into the integer portion.
Yeah.
Okay.
And this is something you do even when, whenever you're picking the mid value, whether you're doing binary search or merge sort or whatever you're doing.
Yeah. This is the best way for finding the mid, right?
This is a safe way. Yeah. This is a safe way. And when you do it this way, it conveys to the interviewer that you're also aware of overflow issues.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today